Hi everyone and welcome to our Unit 1.5 on complex numbers. This discussion is still under the set of complex number system, but for the past few weeks, you know that we've been discussing most on the set of real number system, which would be about the radicals, the rules on radicals, how to operate them, and including the exponent rules. So where do we start in terms of solving complex numbers? If you remember, when we try to solve something like x squared plus 1 equals 0 as an equation, you end up subtracting negative 1 both sides. So you have x squared equals negative 1. Apply square root both sides. And in this part, where you're ending up with a negative radicand, solutions like this gives us an imaginary number. Okay, as mathematicians, they define this as solutions on imaginary numbers. So let's try to understand how we solve them, how we simplify them in terms of these types of imaginary numbers. So to start with, an imaginary unit is considered to be I. So anything that has an I is considered an imaginary number. And it is defined as a value equal to negative 1. Now this is useful when working with square roots of negative numbers. So that's why we discussed radicals first, because you must master first how to solve radicals before entering the world of imaginary numbers, because you'll be dealing with a lot of radicals in here. Now, excuse me. So the pure imaginary number is written in the form bi, where b is considered the real number part and I is the imaginary part. So let's have some examples where we try to rewrite or simplify negative square roots. So the steps are, we rewrite it as square root of negative a as negative 1 times that a, break that a down if it's not a perfect square, and try to simplify the radical using the rule that square root of negative 1 is I. So let's start with this one. When we have square root of negative 9, we could rewrite this as square root of negative 1 times square root of 9. Now you know that square root of negative 1 gives you an I, and square root of 9 is a perfect square, which gives you 3. In this example, you end up with 3i, where 3 is the real part and I is the imaginary. And then this is your simplest form. Okay? Again, you want to make sure that you start first with a numerical coefficient and end up with an I if you extract them in your radicals. Now doing square root of negative 196, we could split that as square root of negative 1 times square root of 196. Recalling your rules in radicals, we know that 196 is a perfect square. We end up having 14 times 14 for this one. Therefore, if we extract them in the radicals, this gives you an I. 196 gives you a 14. Therefore, your final answer is 14i. Again, 14 here is the real part. I is the imaginary, giving you an imaginary number, 14i. Same with negative 5. Square root of negative 5, you end up with square root of negative 1 times square root of 5. Now notice that 5 here cannot be extracted. So the only thing that you could extract in the radical sign is just square root of negative 1. So you will be writing I outside the radical sign and just write the remaining number or the leftover inside the radical. So this is your simplest form for number 3. Let's try square root of negative 80. So square root of negative 80, again, we have square root of negative 1 times square root of 80. Using your rules and radicals, we could do your factor tree. Like this would be 8 times 10. 10 would be 2 times 5. 8 would be 4 times 2. And then you could see that this is just 2 times 2 times 2 times 2 times 5. And since this is a square root, you know that you could extract groups of 2. You want to ask yourself, how many groups of 2 can you extract? So I have 1 pair, 2 pairs, which means I'll be ending up with 2 squared outside the radical sign. I extracted I, and I have a leftover of 5 inside the radical sign, which means my final answer would be 4i square root of 5. Okay, same application for square root of negative 32. You know that negative 32 is not a perfect square. That gives you a factor of square root of negative 1 times square root of 32. Try to factor 32, you end up having 4 times 8. This will give you 2 times 2, 2 times 4, and this is 2 times 2. So you have 1, 2, 3, 4, 5 numbers, 4 2's in the prime factorization. So again, this is a square root, so you want to group them by 2's. So how many groups of 2 can you extract? You have 2 groups of 2, meaning when you extract that, it gives you 4. Don't forget your I. And then you're left with 2 inside the radicals. That's your final answer. So same with this, you end up having square root of negative 1 times square root of 192. You know that 192 gives you 3 times 64. Notice you could stop here if you see that 64 here is a perfect square, because we know that 64 is just 8 times 8. So we could extract 8 as a group of 4, as a pair. It's a square root, right? So that gives you 8 being extracted, and then you have I with that 8, and then you have a remaining 3 in your radical sign. Again, the examples I've shared here are simplifying your basic radicals, and you are ending up with imaginary numbers. Okay, so based on the set of numbers we discussed on the first few days, you know that when we follow the imaginary number was originally coming from a complex number. If you remember the form of the complex number, that is the a plus or minus bi, right? Where a here is just the real part, and we say that bi is the imaginary part. So some examples here would be like x minus 2i, 5 plus 3i. You could also have negative 2 minus 6i. I could have square root of 2. Even if that's irrational, we know that an irrational is also real. So you could end up having that kind of complex number. So complex numbers are not similar with, is quite similar with how you graph your basic points on your rectangular coordinate system. But we have to remember here that since we're dealing with imaginary numbers, we are now using a complex plane when we try to graph them. So complex numbers in rectangular form can be graphed on the complex plane, with the y-axis being the imaginary axis and the x-axis being the real axis. So the real part here, which is the a part, tells you the horizontal component of the graph, and the imaginary part is the vertical part of the graph. Okay, so we use this term in terms of I in math, but when you do electronics later on, the letter J is used when you're using imaginary. So let's have an example where you try to graph a complex number in a complex plane. So let's have an example where you have 3 minus 2i. So again, we follow this form as a plus minus bi. The real axis part here drawn horizontally will be your a part, and the vertical one will be your bi. So if I graph 3 minus 2i, I go 3 to the right, because that's positive. And then I go negative 2i, which goes down 2 units for the I. Therefore, that's your point. Okay? So you could erase this part and just basically plot the point for 3 minus 2i here. Okay? So that's how you plot them. Okay, moving forward, let's try to practice graphing them. You could pause this video and try to graph first letters A to E, following the ways of graphing on a complex plane. So again, we follow that this one would be your A, which is the real part, and the BI would be the horizontal part. So let's start. 3 plus I will be here. Move 3 units to the right. I is 1 unit up, so that would be your point A. B will be negative 2, and then plus 3i, which would be here. That would be your B. So in letter C, in this case, in the form a plus minus bi, we notice that we only have the bi. So what does that tell you with the value of the real axis? It means that a is 0, and you added up 3i in the I in the graph, which means this is your point C. Okay, now we have 1 minus 2i. 1 minus 2i is positive 1 for the right, negative 2i on the vertical graph. So which means this would be your point D. And for E, you have negative 2, but you did not have any values of I, which means that would be your point E. Again, this is the way of graphing complex numbers in a complex plane. Always remember that. In relation to that, there's a term that we use, modulus. Modulus is a term that we use in complex numbers. So when graphing a complex number, we can create a vector from 0, 0, 0, which is this point, and then directly connecting that point from the origin to the point xy. So this is your xy point. Now the length of the vector here is called the modulus. So the blue line that you're seeing here is what you call the modulus, and it's found using this formula. So we follow the formula where this modulus is represented as absolute value of r, which is equal to the square root of the squares of x and y. So if you're very familiar with Pythagorean theorem, this is the way we derive this one. And if you look at the drawing, we have somehow created a right triangle in here. Now the angle that you formed here is called the argument. So this angle here is what we call the argument. Now angles in relation to this topic will not be further discussed, but probably when you go to trig, you will be covering some of that. Okay? So again, this is how you solve for the modulus of a given. Let's try to have an example. Let's say I have an absolute value of 3 minus 2i. How would you get the absolute value of the complex number, or what we call the modulus? So again, we follow the form x squared plus y squared, where x is your numerical coefficient, 3 being squared, plus the numerical coefficient of y, which is negative 2 being squared. Get the square root of that, and that gives you the absolute value of the modulus. So we have 9 plus 4. In short, we have square root of 13. So if we try to graph that, you get 3 here. Let's say this is your 3, and this is your negative 2i. This value of the modulus gives you an absolute value of square root of 13. So again, this process here is the way you solve for the absolute value of a given modulus. Okay. Now we're moving forward with the powers of I. Powers of I is simply observing how the values changes of I. Always remember that when you simplify the form a plus bi, you end up having only I. So if there are powers for the I, you have to simplify that. So this is a certain observation that we want to do when we're trying to observe the values of I, so that we know how to simplify them later on. So based on definition of I, we know that I is just basically equal to the square root of negative 1. So in this example, you just say that I squared will just it's a simple form for I. And again, that's what you want, right? Just I. Now, if you have I squared is just basically I times I, and we know that I is square root of negative 1 times square root of negative 1. And by product, we say that this is just equal to negative 1. So I cubed, on the other hand, we know that this is just I squared times I. We solved for I squared earlier, and we know that that's just negative 1, and I is just I. So therefore, when we multiply these two, we know that I cubed will give you a negative I. I to the fourth is a probable combination of I squared times I squared. We know that I squared just gives you negative 1 times negative 1. So you end up having 1 for I to the fourth. Now that's for the first 4 powers of I. Let's try to observe the next few powers. We have I to the fifth. I to the fifth is just I raised to 4 times I. We know that I to the fourth in the first column gives you a value of 1. and I is just I. So in short, when we simplify I to the fifth, it's just simply I. To do I to the sixth, we'll do I to the fourth times I squared. Again, we're familiar that I to the fourth is just 1. And then I squared gives you -1, so you end up having -1. For I to the seventh, that's I to the fourth times I cubed. You end up having I to the fourth, which is just 1. I cubed is just giving you -I, so when simplified, this is -I. Now I to the 8 is just I to the fourth times I to the fourth. We know that I to the fourth is just equal to 1 times 1, which is 1. Now if you try to look at the pattern here, in the first column, the numbers resulting are just repeating after the fourth cycle. So you have I, -1, -I, and 1, and as it goes, it repeats at I, -1, -I, 1. So it's basically giving you the idea that after the powers of 4, the values are repeating. Okay? So let's try to solve I raised to the 15. If you want to split up into 4s, you could do it at a time. So for example, I to the 15 are just 15 i's as a product, which means if I will try to draw this one or try to explicitly tally this, I'll end up having I times I times I times I, that's 4. I times I times I, 8. I, 12. 13, 14, 15. And you know that for a fact that when you group that 4 i's, that gives you an I to the fourth, right? That gives you I to the fourth, and this is just I cubed. And it's just basically canceling that out, since you know that I to the fourth is just equal to 1. This will just be 1 times 1 times 1 times I cubed. So it's just telling you that I to the 15th can be rewritten as I cubed, and you know that I cubed is just giving you -I. So that's one way to solve that. But remember, you cannot always tally everything because powers could be greater than 15, and you might have a difficult time regrouping them. And the more i's you have, the higher chances that you'll get a mistake tallying them. So another way for you to do that is just to get the multiples of 4 of that exponent. So for example, here I end up having I raised to 62, which means I want to understand how many groups of 4 will 62 have. So if I divide 62 divided by 4, I end up having 1 times 4, that's 4. I have 22. How many groups of 4 can you fit in 22? I only have 5. And there will be a remainder too. So what does this tell you? There are 15 groups of 4, which is just basically telling you that 15 groups of 4 is just I raised to 60, and I have a remainder 2 here. This part here is just equal to 1, because you know that 60 is divisible by 4, and you're just basically solving I squared. You know that I squared is just -1, so you say that -1 is your final answer here. So I think this is very helpful when you try to divide the numbers into groups of 4 and understand how many remainder you have for the powers of I, so you can solve for the exact value of that I. So let's try to do the same thing when we're trying to solve I raised to 76. So I have 76 divided by 4. That gives you 1. 1 times 4 is 4. I end up with 36, and 36 divided by 4 is exactly 9. So what is this telling you? It tells you that as you group the i's, there is exactly no remainder here. You end up having I raised to 0, right? And I is raised to 0 is in the rule of a 0 exponent. Any value raised to 0 is always equal to 1. Let's try to do I raised to 43. You know that if your number sense is good, what's the highest divisibility rule that you could have by 43? That's 40 times I raised to 3. So this basically cancels out. That's just 1, and you're only having I raised to 3, which is just equal to -I. All right, so in the application of this concept, there are ways sometimes where you operate the complex numbers and you're dealing with powers of i's.